First of all, with the idea of, let's say, bond energy. What does bond energy involve? What has to be happening in order to tell us that bond energy is what's going on here? Bond energy is what's important. Yeah, some sort of phase change. If you've got solid turning to liquid or liquid turning to gas or the other way around, then that involves a change in bond energy. There's also the energy change associated with chemical reactions. If you've got molecules splitting up and then forming other molecules, sometimes that's also called bond energy because it involves the bonds within the molecules changing. I usually call that chemical bond energy or just chemical energy to keep them separate, but they do behave in very similar ways in some ways. But for bond energy, if you got a phase change going on, how would you be able to describe how much phase change is happening? What's your indicator for telling you how much energy is transferring or how big of a phase change it is? Usually the mass. What we care about is how much mass changes phase, not just that some ice melts. We want to know how much ice melts. So the indicator, the physical thing you can actually measure that tells you this type of energy is changing, the indicator for bond energy is mass, how much of the substance changes phase. And we specifically are always going to use mass of the higher energy state, higher energy phase. For example, we treat this as gas is the higher energy phase. Gas is the highest energy phase. Gas is higher energy than liquid. Liquid is higher energy than solid. Solid is the lowest energy phase. And the reason we want to choose to use the higher energy phase is to make certain positives and negatives match up more easily or more usefully. For example, let's say we have a certain amount of liquid water. Let's say we have 5 kilograms of liquid water. And we want to boil it or partially boil it. So let's say we end with 2 kilograms of liquid water and the other 3 kilograms are now gas. Steam. And we want to figure out how much energy this takes. How much heat do we have to provide to make this happen? Presumably this is a change in bond energy because it involves a phase change. And we can actually show this on the 3-phase graph. If we draw out the usual 3-phase diagram of energy added versus temperature with the usual shape. And let me label these corners just for reference. If we just call these corners 0.1, 0.2, 0.3, and 0.4 for reference, where would you say the water is to start with? What's the initial condition on this graph?
Is it 2?
Yeah, 0.2. Actually, 0.2 represents what sort of situation?
The solid liquid phase becoming a liquid?
If we start labeling these, we've got a diagonal that represents the solid phase, a diagonal that represents the liquid phase, diagonal that represents the gas phase. The idea being that if it's in a solid form, then you can add energy to raise the temperature. So going diagonally up and to the right means you're adding energy, raising the temperature. When you get to 0.1 though, you add more energy and the temperature doesn't change because what's happening there? Yeah, this horizontal line represents a phase change. During a phase change, you're adding energy to break bonds to allow more freedom of movement, but you're not changing the temperature. During a phase change, typically we would assume the temperature stays constant. So this is going from all solid to partly solid, partly liquid to mostly liquid to all liquid. So at 0.2, it's all liquid, but what temperature would we say it's at?
A constant temperature?
It's at a constant temperature this entire process, but what is that temperature? Do we know what temperature is that?
Point?
Yeah, that's the melting point, P melt, which for water should be 0 degrees. So 0.2 represents water, liquid water at 0 degrees. If we continue to add energy, we continue to raise the temperature. We're going up and to the right, adding energy, raising the temperature, adding energy, raising the temperature, until we get to 0.3. What does 0.3 represent? Yeah, that's the boiling point. So this value on the temperature axis would be the boiling point, 100 degrees for water, 100 degrees Celsius. So at 0.3, it's now liquid at 100 degrees. If we continue adding energy, what's going to happen? Yeah, it's going to go through another phase change. It goes from all liquid at 100 to mostly liquid and a little bit gas, still at 100, to about half and half, and then mostly gas, a little bit liquid, and then all gas. So at 0.4, it's completely gas and still at 100 degrees. Then if we add more energy, the gas, the steam, starts to get hotter and hotter. Again, adding energy to raise the temperature. So each one of these diagonals represents a different phase, but staying in that phase the whole time. And then these horizontals represent changing the phase, but keeping a constant temperature. Any questions on that so far? And I actually didn't specify a temperature here, but let's assume for simplicity that this is 5 kilograms of liquid water already at the boiling point. And we want to end with a mixed phase, which is guaranteed to be at the boiling point. One important thing to look for is that if the result or the beginning, if any situation at equilibrium is all at the same temperature, but in a mixed phase of one single substance. If we've got a mixture of liquid water and gaseous water at the same temperature, that has to be at the phase change point, the phase change temperature. Because if it was any hotter than 100, it would be all gas. Any colder than 100, it would be all liquid. If you've got a mix of liquid and gas at the same temperature, it has to be at the boiling point. Any questions on that so far? So if we're currently all liquid at 100 degrees, which one of these points are we actually at?
Is it 0.3?
Looks like we should be at 0.3, because 0.3 is all liquid. In fact, this entire diagonal is all liquid, but if it's all liquid at 100 degrees, that's going to be at location 3. So location 3 is our initial. And then we're transitioning to a little more than half gas, a little less than half liquid. So where would you say we end up on this graph? We're going from 3 towards where?
Towards 4.
Yeah, we're definitely going towards 4 because we are at least changing some of it to gas. Since we're not changing all of it to gas, we're only going to go partway there. Specifically, it looks like we turn 3/5 of it to gas, so we're going to go 3/5 of the way towards location 4. So we'd have this transition with an arrow to show direction, and then this would be our final stop, our final situation. So that's the portion of the 3-phase diagram we actually care about. We're just going from this location as initial to this location as final. We are mostly, but not entirely, boiling it. And that means that that amount of energy, if we trace the initial and final points to the energy axis, this transition, this change, that is our delta E bond. That's not how much bond energy it has, that's just how much the bond energy needs to change in order to make this happen. So that's our delta E bond there. Whereas if we were going along a temperature change, moving along one of these diagonals, that would be a delta E thermal. Any questions on that so far? So if we wanted to draw that out as an energy interaction diagram, we would just list out all the types of energy that are changing, in this case, just bond energy. Bond energy, and I would specify bond energy of the water boiling. Because in a given situation, there might be several bond energies changing. Maybe there's several phase changes going on. So I would specify which bond energy you're talking about. The indicator is mass. So we're going to use mass as the indicator. And specifically, should we be using mass of the liquid or mass of the gas here?
The gas?
Yeah, mass of the gas, because gas is the higher energy state. And as we go from initial to final, is the amount of gas increasing or decreasing? Yeah, increasing. We end up with more gas than we started with. So we've got an increase in the amount of gas. And therefore, the bond energy is also increasing. One of the reasons why we specifically use mass of the higher energy state is so that the arrows match up on the indicator and the type of energy. The bond energy is increasing because the mass of the higher energy state is increasing. In fact, we can even list out initial and final values. How much gas do we start with?
Would it be 0?
Yeah, we start with no gas at all. We've got 5 kilograms of liquid, but no gas. So the initial mass of gas would be 0 kilograms. And how much gas do we end with? Yeah, 3 kilograms of gas. So the final mass of the gas is greater than the initial mass of the gas. The mass has increased. Of course, the total mass of H2O in this system doesn't change. We're just changing how much of it is in each phase, how that breaks down. It looks like that's the only type of energy changing, because we're not going through any temperature changes, we're not going through any other phase changes, and there's no other objects we're really considering. So this is the entire system. And would you consider this to be an open system or a closed system?
Open?
Yeah, this is going to have to be open. And why is that? How do we know? Yeah, we've got to add heat, right? Even though we didn't really specify that we're adding heat here, how do we know that heat has to be added to make this work, to make this happen? We've got to break the bonds. And it's possible to have bonds breaking in a closed system. But if you take a look at the energies here, we've got one type of energy increasing. Is anything else decreasing to balance that out?
No.
So if you've only got stuff increasing, that energy can't just appear from nowhere. You've got to be adding that energy from somewhere else. So if you only have one type of energy changing, or if all the energies are increasing, or if all the energies are decreasing, you know it has to be an open system. Because if everything's increasing, that energy has to come from somewhere. If everything's decreasing, that lost energy has to go somewhere. So this has to be an open system, because there's no way for the changes to balance out if there's only one change. And heat is going to be entering or leaving.
Entering?
Yeah, we've got heat entering to make the energy increase. So we draw an arrow pointing inwards and label that Q for heat. And then we could even turn this into an equation. We could say that in general, for any open system, if it was a closed system, we'd say change in total energy equals 0. But this is not a closed system, this is an open system, so we're going to say the change is heat plus work. That's really the foundation of all conservation of energy, usually called the first law of thermodynamics. Sometimes jokingly referred to as there's no such thing as a free lunch, because any change in the total energy of the system has to be caused by heat and or work entering or leaving the system. Heat being a transfer of energy caused by, what causes a flow of heat? Why does heat flow from one place to another?
Maybe like an equilibrium?
It's approaching equilibrium, right? And what has to be already present in order for it to not already be at equilibrium? Like physically, how would you make this happen? If you've got just 5 kilograms of water, what would you physically do to it to make it start boiling?
Apply heat.
What is heat though? How do you make heat enter the system? Like what would you physically do to this to make sure that heat enters the system instead of leaving the system, or neither one?
I'm not sure. Maybe like excite the particles, like speed them up.
Is that what you do when you want to boil water? Like you reach in and start wiggling the particles around?
No, like put it on a flame.
Yeah. Step away from the lab for a minute and think about this more pragmatically. You want to boil water, you put it on a flame. Because the flame is, what property does the fire have, the fiery object have, in comparison to the water?
It has more heat.
Heat isn't really something it has, though. Heat is a transfer of energy.
Higher temperature?
Higher temperature, yeah. The fiery object, the burner or whatever you're putting this in contact with, has a higher temperature than the water already has. Heat is specifically the flow of energy from a high temperature object to a low temperature object. Heat flows from hot region to cold region. So if you want heat to flow, all you need to do is put two objects or two regions in contact with each other that have different temperatures. And heat will naturally flow from the high temperature zone to the low temperature zone. Equilibrium just means that all that heat has finished flowing and the objects are now at the same temperature. So no more heat will flow. But if you want heat to flow, you need a difference in temperature from one location to another. As opposed to work, work represents a transfer of energy due to mechanical means, like due to forces on moving objects. Specifically, if you have an object and you push on it while it moves, a push or a pull, a force on a moving object is work. So if you just got an object that's moving, but you're not applying a force, that doesn't count as work. If you're pushing on an object, but it doesn't move, that doesn't count as work. But if you're pushing on an object while it moves, you are doing work. And that work is a mechanical transfer of energy, as opposed to heat, which is the transfer of energy caused by a temperature difference. But they both still count as transfers of energy. In this case, we're not pushing on the water, we're just applying heat by putting it in contact with something hotter than itself. So we can ignore work and say we just have equals heat. And the only type of energy changing here is the delta E bond. So in this specific case of just the bond energy changing because we're applying heat, we can say delta E bond equals heat. You're applying heat, and the amount of heat you apply is the change in bond energy. If we want to figure out the actual amount of heat, we're going to need a formula for delta E bond. And do you have a formula for delta E bond yet? Or alternatively,
I don't think
let's see if we can
I don't think she's explicitly said it in lectures yet.
Then let's see if we can build one. We know that it should depend something on the mass of the object, presumably, I mean, partly because that's the indicator, but also the more you want to change phase, the more mass you want to change phase, the more energy it should take. Like it's going to take a certain amount of heat to boil 3 kilograms of water. If you wanted to instead boil 30 kilograms of water, it's going to take a lot more energy. Specifically, how much more energy would you expect if you were boiling 30 kilograms instead of 3 kilograms? Presumably 10 times more. If you're boiling 10 times as much water, it's going to take 10 times as much energy to do it. We can assume, and this turns out to be correct, we can assume that the energy change, the change in bond energy, is proportional to the mass, or rather the change in mass. Delta M in the sense of how much mass is changing phase. In this case, final minus initial, 3 kilograms minus 0 kilograms. So the amount of energy it takes to boil a certain amount of the substance is proportional to how much of the substance you're boiling. And what do we mean by proportional here? If we say two quantities are proportional to each other, this sort of alpha-like symbol, what does that actually mean?
Doesn't that mean like if one increases, the other has to increase as well?
Partly yes, but even more specific than that. Not just that the other one increases, but that it increases by the same ratio. Like as we were talking about earlier, if one of them increases to 10 times the original value, the other one also increases to 10 times the original value. Or if you divide one of them by 3, the other one also gets divided by 3. They're changing in the same way in terms of multiplication and division. Not in terms of addition. Like if you add 5 to one of them, that doesn't mean you're adding 5 to the other one. But they're changing by the same multiplier or changing by the same divisor. In fact, that's usually I would say the intuitive understanding of or what the conceptual idea of what proportionality is. Proportionality means that they're changing at the same rate, changing with the same ratio. But we can also turn proportionality into an equation. In general, if two quantities are proportional, let's say if y is proportional to x, we can always write that as an equation. Specifically, we can say that one of the variables equals what? Have you seen how you could turn that proportionality into an equation? In general, if two quantities are proportional, you can always write one of them as being equal to the other one times some constant. Like maybe y happens to be 5 times x, or maybe y is 3/2 times x or something. Or maybe it might even be a negative constant. Maybe y equals negative square root of 2 times x. But proportionality always means you can write one of the variables as equal to the other one times some constant, usually called the constant of proportionality. So if we're claiming that delta E bond is proportional to delta mass, that means delta E bond is going to be equal to delta mass times some constant. And this is always true for proportionality. Anytime you know two quantities are proportional, directly proportional, you can always write that out as an equation. One of the variables equals the other variable times something. And that something is usually some important property of the system you're talking about. In this case, that something, that constant of proportionality, is called it's called different things in different textbooks. Sometimes the enthalpy of boiling or melting, or the latent heat of boiling or melting. In this textbook, 7 series textbook, we're going to call it delta H. And we're typically going to call that the enthalpy of, in this case, the enthalpy of boiling, or heat of boiling, or heat of vaporization. It's got various different names, but it just means the thing you multiply by delta mass in order to find delta E bond. And what do you think that would depend on? What other things do you think would determine what that coefficient is going to be in terms of actual value? Like for instance, let's say you take a 5 kilogram object and you boil it, and it takes a certain amount of energy. If you take another 5 kilogram object and boil it, can you guarantee it will take the same amount of energy? What other properties could be different that would lead to different amounts of energy to boil 5 kilograms? Not necessarily heat capacity or boiling point. That really has more to do with temperature changes. But let's say you've got a 5 kilogram object and you want to change its phase. And you've got another 5 kilogram object and you want to change its phase. Let's assume they're already at the phase change point. What is it about those objects that could lead to different amounts of energy required to melt them or boil them?
Is it that they're different objects?
Let's assume they're the same mass. But what else could be different about the objects other than the mass?
Maybe they're in different phases.
Could be in different phases. Maybe we're talking about solid to liquid versus liquid to gas. But also, what if they're, let's say, a 5 kilogram block of ice versus a 5 kilogram block of iron? Are those going to take the same amount of energy to melt? So if you take 5 kilograms of anything, does that always take the same amount of energy? They could be different, right? They're different substances. The delta H, as it turns out, is a property of the material it's made from. So different materials, different substances have different values for delta H. And that has something to do with the density and also something to do with the structure of the molecules themselves, how tightly they're bonded together. So delta H is a property of the material. So for instance, there will be a delta H value for ice melting, a different delta H value for liquid water boiling. The different phase changes, even of the same substance, have different values. So you could have delta H for ice melting, delta H for liquid water boiling, delta H for iron melting would be a different value, delta H for copper melting would be another different value. Every substance has a delta H value. And you can find that delta H value, the enthalpy of melting or boiling or whatever, algebraically. In fact, a very useful approach, anytime you're introducing a new constant, a new idea in an equation, like we just built this new equation with this new coefficient, this new constant of proportionality. Anytime you introduce a new constant of proportionality, there are a few things you ought to do to get more information about it. One thing is, if you've got a constant or variable in an equation, how can you get more information about that specific constant? How can we find out what delta H means in this context? What tool from algebra could we use to get more information about a certain constant or variable?
You could isolate H.
Yeah, exactly. We could try isolating delta H. And don't worry too much about the delta here. I would just think of delta H as just one package. This is a value that we're calling delta H. But let's try isolating that. How would you isolate delta H here?
Divide both sides by delta M.
Yeah, if we divide both sides by delta mass, we get delta E bond over delta N. So this is what delta H means. Delta H is this ratio of how much energy it costs divided by how much mass changes phase as a result. So delta H is a rate of change. How much energy divided by how much mass changes phase as a result. And a very useful way to think about ratios like this, what's the easiest number to divide by? What's the easiest denominator to use here? Yeah, if we treat the denominator as 1, because this could be any amount of mass. We could say, let's take exactly 1 kilogram or 1 unit, whatever units we're using, 1 unit of mass. Delta E bond divided by 1 is just going to be delta E bond. So a very convenient way of thinking of delta H is just the amount of energy it takes to melt or boil exactly 1 kilogram of the substance, exactly 1 unit. In fact, this is a very convenient approach for anything defined as a ratio. Any quantity that's defined as a ratio of delta somethings, just pretend the denominator is 1. The result is the amount of numerator required to get exactly 1 unit of denominator. So delta H, the enthalpy of melting, 1 of whatever units of measurement you're using. So delta M might be measured in kilograms or grams or megagrams or whatever unit of measurement you want for mass. So delta H is the amount of energy it costs to change the phase of exactly 1 whatever units of measurement you're using for mass. Typically, we're going to be using kilograms, but it doesn't have to be in kilograms. It could be in whatever units you're using. But we want it to be standardized. We want to be using the same units throughout the whole problem. And typically, it's going to be listed in terms of kilograms. Also, what is energy measured in? What's our usual unit of measurement for energy?
Joules.
Yeah, joules, capital J. So that means the units of measurement here, which is another important thing to check anytime you're introducing a new quantity. You want to know what are the units. The units for delta H, enthalpy of melting, are going to be joules per kilogram. Or since we're often using, it's often going to be very large numbers. It typically takes a lot of energy to get a whole kilogram of something to melt. So we're often going to list this in kilojoules per kilogram. So joules per kilogram or kilojoules per kilogram to make the numbers easier to work with. That's the typical unit of measurement for delta H. And I think it's very useful to think of this as a difficulty or a cost. That if you want to melt something, a large delta H means it takes a lot of energy to change the phase of 1 kilogram. A small delta H means it only takes a little bit of energy to change the phase of 1 kilogram. So large delta H means difficult to change the phase. Small delta H means easy to change the phase. And for instance, if delta H is, let's say, 50 kilojoules per kilogram, that means it costs 50 kilojoules of energy to melt or boil 1 kilogram of the substance. And you could calculate that in a lab. If you have the means of measuring an amount of energy and measuring an amount of mass, you could just apply exactly enough energy to melt 1 kilogram of the substance. That amount of energy per kilogram is delta H. Any questions on the meaning of that so far?
Oh, I had a quick question. So like what exactly does enthalpy mean?
Enthalpy it's related to energy. It's really more about energy. It's energy with, what's a good way to put it? We're going to get into this in more detail later in the quarter. Yeah, it's a good, one good way to think of it is energy, but ignoring the amount of work, if we're looking at just the amount of heat.
So it's just like heat.
It's related to heat. The change in enthalpy is basically an amount of heat.
Okay.
More formally, enthalpy is a measure of both how much energy a substance has and how much space it takes up. Pragmatically, it's the change in enthalpy is just an amount of heat under certain circumstances. And we're going to get into more detail of this when we get into ideal gases later in the quarter. But
Okay,
for now,
thank you.
for now, I would say delta H is just this quantity that's a property of the substance. So there's a delta H for water melting is just a number associated with water that tells you how difficult it is to melt ice. Or delta H for water boiling is a number associated with the substance that tells you how difficult it is to boil water to make steam. But since it's associated with the substance, we don't really need to do this experimentally because we're not, for instance, the first people to ever wonder what's the delta H of water boiling. This has all been done millions of times in labs all over the world. And these values, delta H for water boiling, for instance, are already well known and standardized. And so instead of running experiments with this, if you just want to know how much energy does it take to boil 3 kilograms of water, you could just look that up on a data table. So we could take a look at, for instance, here's a data table listing the properties, the melting point, boiling point, and for our purposes, most importantly, the heat of vaporization. Heat of vaporization, this one here, tells you how much energy it takes to boil 1 kilogram of the substance. So we can just look that up for water. So if we look that up, for water, we've got actually 2 values listed. I list this as 2,257 kilojoules per kilogram, or as 40.7 kilojoules per mole. So it lists 2 values. Where can we find the list? If you have, this is the old physical copy of the Physics 7A textbook. If you got a 7A digital textbook, I'm pretty sure it should be in there. Otherwise, they'll probably provide you with one as a separate document, or you can find one online. If you just look for a table of heat of vaporization values or heat of melting values. I'll see if I can put one on mathandcheese.org as well. Since we've got 2 values though, how do we decide which one of these to actually use?
Isn't like the moles one, like isn't that when we're dealing with like chemical reactions and stuff like that?
Well, the thing is, these are both of these are valid ways of describing it. It's just 2 different ways of describing how much. This one is describing how much energy it takes to melt or boil, or in this case, boil exactly 1 kilogram of the substance. This one tells you how much energy it takes, 40.7 kilojoules, to boil exactly 1 mole of the substance.
Oh, okay.
But if you take a look at the situation we've got, would kilograms or moles be a better match?
Probably kilograms.
Yeah, the units of measurement we already have are already in kilograms, so we may as well use the measurement that matches up, the one that's already in kilograms. If we wanted to use the kilojoules per mole version, often called the molar enthalpy, or the molar heat of vaporization, the amount of energy to vaporize 1 mole, we'd have to start by converting the kilograms to moles, which would be inconvenient. If we've already got the unit, this measurement in the same units of measurement of what we've already got, we may as well use that. So I will use the 2257 here because it's already got the same units of measurement. The other one is mostly useful for an alternate version of delta E bond formula. You can also say delta E bond, instead of writing it as amount of mass changing phase times some constant, you could write it as amount of moles changing phase, usually written as delta lowercase n times delta H. And in that case, we usually call it delta H sub mole. Delta H sub mole means the molar enthalpy of vaporization, how much energy it takes per mole rather than how much energy it takes per kilogram. So these are both describing the same core idea, amount of energy it takes to change the phase of 1 unit. It's just that the units could be described as amount of kilograms versus amount of moles. So same idea, just different per whatever units of measurement. Energy per mole versus energy per kilogram. Any questions on that so far? And typically data tables like that will often have like 2 columns side by side, one listing it in terms of kilograms, one listing it in terms of moles. You just want to use whichever one of those matches up with the units you already have and or the units you're trying to get the answer in. In this case, we're dealing with mass. So I'm going to write delta E bond as delta M delta H. And we can now fill in some of the values. Typically, I would start by solving algebraically for whatever you're trying to find. In this case, though, we know how much mass changes phase. We already looked up delta H. The only unknown left is heat. So we don't really need to solve for heat because heat is already isolated on one side of the equation. If you did need to isolate one of the variables, I would do this now before plugging in any numbers. So we've already got Q by itself here. So Q equals, and delta M, how would you calculate the delta mass, the change in mass?
The final mass minus the initial?
Right. Delta anything can typically be calculated as final minus initial. So subtracting final minus initial, that's going to be 3 kilograms minus 0 kilograms, which is just going to be positive 3. Note that that positive is going to refer to the idea of the heat being positive. What does it mean if heat is a positive value? What does the sign on heat mean? The idea of heat being positive versus negative. Yeah, the system is gaining heat. Heat is entering the system, making its energy increase. So a positive value for heat, heat being a positive value, means heat is entering the system. The system is gaining energy as a result. On the other hand, if we had been, let's say instead of boiling the water, let's say we start with steam and we condense the steam back into water. We'd end up with less steam. So we'd start with lots of steam and end with less steam, which means what would we get when we subtracted to find delta M? You'd get a negative value. And what does a negative number mean for heat? If heat is a negative value, then that means, right, you're losing heat. Heat is leaving the system. And that's what you'd have to do if you wanted to condense it. If you want to go from steam to liquid water, you've got to remove heat from the system. So as long as you're always subtracting with the mass of the higher energy state, final minus initial, any positives or negatives you need will automatically be built in. You don't need to worry about manually assigning plus or minus because it will already automatically achieve the correct sign, as long as you're always using mass of the higher energy state. And let's finish that off. We plug in the delta H, 2257 kilojoules per kilogram. So we get 3 times 2257. And what's going to happen to the units of measurement there? If we've got kilograms multiplied by kilojoules per kilogram,
You're gonna be left with kilojoules.
exactly. The kilograms cancel out. We're left with just kilojoules. Multiply that out, we get 6,600, 6,750, 71. So this would be the amount of heat required. Then in order to make this happen, in order to boil the 3 kilograms of steam while leaving the other 2 kilograms still liquid water, we would have to apply 6,771 kilojoules. Kilo meaning 1,000, so that's really 6,771,000 joules. But typically we would just leave the answer in kilojoules. Doesn't really ultimately matter whether it's in joules or kilojoules or megajoules, as long as you're consistent about it and make sure you label the units properly. Any other questions on that so far?
Can you explain again where you got the change in H value?
The delta H here,
Yeah.
that was from looking it up on the data table.
Oh, okay.
The idea is for any known common substance, water, mercury, iron, oxygen, nitrogen, whatever, all of these delta H values are well-known, standardized, and you can find them on a typical data table. So there's data tables available of delta H values for lots of common substances, both the melting process and the boiling process. And if you want to go in reverse, like if you just want to, if you start with a gas and you want to condense it, you would still use the same delta H. This delta H covers the transition between liquid and gas regardless of direction. If you're condensing gas, if you're going in the other direction, delta M will turn into a negative number when you actually subtract final minus initial, but you still use the same delta H. On the other hand, the transition between solid and liquid is going to have a different delta H because melting a substance and boiling a substance typically take very different amounts of energy. Because if you're going from solid to liquid, you're breaking some of the bonds. Going from liquid to gas, you're breaking all the rest of the bonds. Any other questions on that so far? And let's take a quick look at thermal energy as well, since we've got a few minutes left. Thermal energy is covering a different portion of the three-phase diagram. Let's say you're going through a temperature change. Let me actually reset this. And let's say we're just looking at a portion of this. Maybe there's more of the graph elsewhere. But let's say you're just going from, let's say, this temperature to this temperature. So we have an initial temperature, we have a final temperature. In that case, we have a starting energy, we have an ending energy, and this change would be what type of energy change?
Thermal.
Yeah, that's delta E thermal. And what's the indicator for that?
Temperature.
Right. We know that there's a change in thermal energy because there's a change in temperature. And we should also expect those to be proportional. Delta E thermal should be proportional to delta temperature. If you want to change the temperature by a certain amount, it costs a certain amount of energy. If you want to change the temperature by 5 times that much, it's going to take 5 times as much energy, and so on. So by the same token of proportionality, we can still assume that one of these equals the other one times some constant. Delta E thermal should equal some constant times delta temperature, because that's what proportionality means, mathematically speaking, that one of the things equals a constant times the other thing. And that constant is something we call the heat capacity, usually written as a capital C. So the heat capacity of the object is this thing, this constant you can multiply by the temperature change you want in order to calculate how much energy it's going to cost to make that temperature change happen. And what would you generally expect if you were graphing, like if you think of temperature as input and energy as output, if you graph output equals a constant times input, what sort of graph is that going to make? What shape on the graph? It would be linear, right? And what would this constant tell you about that line?
The slope.
Exactly, that's the slope. And we in fact have a graph of energy and temperature. It's kind of backwards because we've got temperature on one axis and energy on the other axis in sort of the wrong way. If you solve this for heat capacity, what would you get? Again, to get more information about it.
Divide by change in T.
Right, divide by change in temperature, we get change in energy divided by change in temperature. So this is the definition of heat capacity. Heat capacity is the change in thermal energy per degree of temperature change. And this is almost the slope of this graph. The only difference is if you actually calculated the slope here, rise over run, what would the rise be? Rise is the change in what?
Temperature.
And run is the change in?
Energy.
Right. So the slope of the three-phase diagram is rise over run, change in temperature divided by change in energy. That almost looks like heat capacity, except for what?
It's thermal energy.
It is specifically thermal energy, yes. But also, even ignoring what type of energy, what else is different between this formula versus this formula?
It's the reciprocal.
Exactly. It's the reciprocal of the heat capacity. So they're related, but they're not exactly the same. The slope of this graph is 1 over the heat capacity, the reciprocal of the heat capacity. So a large heat capacity would mean a very flat diagonal line. A small heat capacity would mean a very steep line on this graph. And again, you can think of this as a difficulty level. Large heat capacity means it costs a lot of energy to get a small temperature change. Small heat capacity means it takes only a little bit of energy. It's very easy to get a temperature change. And what would the units be for that? Energy is measured in what?
Kilojoules.
Yeah, joules or kilojoules. And then temperature is measured in?
Kelvin.
Yeah, it could be Kelvin or degrees Celsius. It's typically going to be listed as Kelvin, but degrees Celsius also works. The thing is, we're talking about a change in temperature. If you're talking about change in temperature, Kelvin and Celsius are the same. Like increasing the temperature by 5 kelvins, increasing the temperature by 5 degrees Celsius, it's the same change. So if you're talking about a delta temperature, you can use Celsius or Kelvin as long as you're consistent about it throughout the entire problem. Make sure either everything's in Kelvin or everything's in Celsius. Although if you have a temperature without a delta attached to it, that has to be in Kelvin. But with a delta, it can be in either one. Just be consistent. Any questions about that? All right, we're going to look into heat capacity and thermal energy in more detail next time. In the meanwhile, you might take a look at those data tables if you can find some, and you'll notice that heat capacity as it is doesn't really show up on those data tables because the heat capacity depends on one other thing other than just the substance. So try thinking about that over the weekend. What about the object would cause it to cost a certain amount of energy per degree Celsius of temperature change? Why do different objects have different heat capacities? So think that over, try applying these ideas to the problems on your FNT. Let me know if you have any other questions online, and I will see you next time.
Thank you.
You're welcome.
Thank you.